All right. So let's look at this function. We're going to graph it first. So we're going to graph the function f of x equal to the following piecewise function. It is x squared plus 1 when x is less than or equal to 0. It is x plus 1 when x is bigger than 0 and less than 3. And it is the square root of x plus 1 when x is bigger than or equal to 3. And so we can graph this. Is not too terrible. Sorry, it's very windy outside my house right now. I can keep hearing like things moving around out there. You should try not to be too distracted though. So x squared plus 1 is just your usual parabola shifted up 1. And I want that up until x, so where x is less than or equal to 0. So when x is 0, 0 squared plus 1 is 1. So I get that point there, and I get everything to the left, where x is less than or equal to 0. And then y equals x plus 1. You know, it looks like a line increasing from left to right, with a slope of 1. If I could plug in 0 here, I would get 1, right? Because 0 plus 1 is 1. So I would actually get the same point. And then if I could plug in 3 here, I would get 3 plus 1, which is 4. And then finally, the last piece, which is square root of x plus 1 when x is bigger than or equal to 3. That looks like your usual square root function. Shifted 1 to the left, shifted 1 to the left, right? So I'm actually going to draw too much of this, right? This would look like if x was 0, sorry, if x was negative 1, I would get 0. And then when x is 0, I would get 1. And then when x is 3, I would get 3 plus 1 is 4, square root of 4 is 2. So it would look like this, but it's not actually starting until I get to 3. Right, and it looks kind of straight the way I've drawn it, but it's supposed to be more curvy. And we don't want any of this. Okay. So I'm going to ask you guys a question. It should be very easy to answer. Just looking at this thing visually, when x is 0, does this function look like or does this function look like it's continuous when x is equal to 0? Yeah, totally. In fact, you guys could even, if you want, right, you could use the fun little participant responses. You could click on yes if you wanted to, or you could click on no if you thought it wasn't, but it is. So you don't have to, but you could. And then, how about at 3? Does it look like it's continuous or not? Right. Definitely not continuous. But let's talk about the whys and the hows. So I should say more generally, and this is kind of a language thing. If someone asked you, is this function continuous? Well, first of all, that wouldn't be a very good question. But if someone did ask that question anyway, I would say, no, this function is not continuous. And what I mean when I say that it's not continuous is I mean that it's not continuous everywhere. So when someone asks if something is continuous or discontinuous, or something, I should say, someone asks if something is specifically continuous, they typically mean, is it continuous everywhere? And so the question I really should be asking is, where is this function continuous? And really, when we ask this question, where is f of x continuous? The question we're really actually asking is, where is f of x not continuous? Because we're going to find all the places it's not continuous. We're going to exclude those from everywhere else, and then everything left over is going to be where the function is continuous. So here's the nice thing. Each of these individual pieces, x squared plus 1, x plus 1, and the square root of x plus 1, excuse me, they're all continuous on their domains. These first two are actually continuous everywhere, right? X squared plus 1 and x plus 1 are both polynomials. And polynomials are always continuous everywhere, which is great. Square root of x plus 1 isn't continuous everywhere. It's not continuous where it's not defined, but it certainly is defined when x is bigger than or equal to 3 on this domain here. So each of these pieces of this piecewise function are individually continuous on their own domains. The issue that you might already be aware of, shouldn't have drawn that in red. It feels weird that I've drawn that just like, okay, this looks weird. Let me fix that. Sorry. The issue here is that while each of these pieces are continuous on their own domains, when you switch from one piece to the next piece, you might have a point of discontinuity. We don't here. When we switch from here, this piece to this piece, we do get discontinuity of 3. So typically, in a piecewise function, the places where we're most concerned about the possibility of being discontinuous are the changeovers. When you change from this function to this function, at x equals 0, and when you change from this function to this function, at x equals 3. And so we're going to see if they're continuous in the usual way. I should say, we're going to see if this function is continuous at those points in the usual way. So let's first look at x equals 0, which we're already pretty sure it's continuous at because we've drawn the picture and it looks continuous there. That's not a substitute for showing it's continuous using the definition. So you can totally draw this picture and say it's continuous at 0, but if someone asks you to use the definition of continuity to show it's continuous, that wouldn't be sufficient. So here's how it actually do it. Step 1. Sorry. What do I want to say? So plug, right? Does f of 0 exist? So can I plug in 0? Of course I can plug in 0. I'm going to plug it into the place where x is equal to 0. I'm going to get 0 squared plus 1. Step 2. We need to check that the limit exists. And for most of these piecewise functions, not always, but most of the time, for a piecewise function, you're going to have to deal with the different one-sided limits. So here, the left-hand limit as x approaches 0 and the right-hand limit as x approaches 0 are going to be different things we have to evaluate. They end up being the same value, but they definitely have different functions. So when I look at the limit as x approaches 0 from the left of f of x, when I approach 0 from the left, that means I am less than 0 or left of 0. It's nice that less and left both start with the letter L. When you're less than something, you are left of it on the number line. So if I'm going to be left of 0, I have to be less than 0, which means I'm using this piece of the function. So it's the limit as x approaches 0 from the left of x equals 1. And then a lot of the time with these piecewise functions where we're trying to find continuity, we can just use the direct substitution problem and say, okay, well, I take the limit as x approaches 0 of x squared plus 1, I plug in 0. And get 1. And then we do it from the other side. So, sorry, I kind of wish this board sometimes was a little bit higher. So sometimes I'm just like walking around on my knees and not always super fun. I mean, sometimes it's fun, but sometimes it's not. So let's do the limit as x approaches 0 from the right. As x approaches 0 from the right. So this is, I've definitely seen people get caught up on this part. This just says x is bigger than 0, but I've definitely seen people pick this piece of the function. Because technically x is bigger than 0 here. But really, when I say x approaches 0 from the right, it means we're on the right side of 0, or bigger than 0, and we are close to 0. That means we have to use this piece, where x is just bigger than 0 right here. So that's that. So the limit as x approaches 0 from the right of f of x is the limit as x approaches 0 from the right of x plus 1. And again, I can just plug in 0 and get 0 plus 1, which is 1. Now, I should point out, and I've definitely seen people make this error as well. I've seen a lot of people say that if the limit exists, that means the function is continuous. That's not wholly sufficient. It's definitely a necessary condition. But for the function to be continuous at a point, the limit has to exist, the function has to exist, and most importantly, they have to be equal to each other. So typically at the end here, which I've kind of run out of room, let me write it up here. So here's part 3. Here's what I would say for part 3. I would say that f of x is continuous at x equal to 0 because the limit as x approaches 0 of f of x exists and is equal to f of 0. That's really what we're striving for, to show that the function is continuous at a point. Now, I really should mention as well, I'm not going to show continuity at every point it's continuous. I couldn't, right? There's an infinite number of points. I'm not checking anything that's not one of these breakpoints because I know this function is continuous where it was on its domain, as is this, as is this. So let's now deal with the point that we're pretty sure is discontinuous. And the next part I'm going to do, the way you need to do it might kind of vary on what your teacher wants you to do. But I'm going to kind of show you the whole picture and then tell you how you might be able to do a little bit less work. Also, if you have specific questions you want to see me work on, or one similar specific questions you want to see me work on, let me know. Let's see if I can get that. Sorry, I need to. I guess I've literally got it on the computer here. Yeah. Just so I don't have to keep looking back at the time. Okay. So now we're asking, is this function continuous at x equal to 3? And you might know what's going to make it not continuous. I still like to go through the process that I've typically gone through, which is first see if it exists at 3, then see if the limit exists, and then if they both exist, see if they're equal. That's usually the process I like to go through. So, oh yeah, there was something. Let me look at where'd you go? I wrote myself a note earlier about something and I just want to check it. There was something. Oh yeah, okay. That's later. Sure. So sorry, words. I want to first see, does f of 3 exist? Yeah, and a lot of the time, usually this isn't going to fail, although it can. So f of 3, I'm going to plug it into the one where x is equal to 3, which is the bottom one here. So that's going to be equal to the square root of 3 plus 1, which is 2. So part 2, does the limit exist? So I have to look at the limit from either side. And here's the way you could do the least amount of work and still reach a justifiable conclusion here. If I look at the limit as x approaches 3 from the side that doesn't use the same piece of the function. So I'm looking at the limit as x approaches 3 from the left, because that's going to use this piece, which is not the same piece. So I'm doing the limit as x approaches 3 from the left of f of x, which is the limit as x approaches 3 from the left of x plus 1. If I just evaluate, so I should also mention, so I feel like I'm saying that a lot. I should also mention, because I've seen this a lot too. If you're approaching 3 from the left, it doesn't mean you're plugging in 2 or 2.5 or 2.9. You can do those things to see what the things getting closer and closer to, but really you are getting as close to 3 as humanly possible, like 2.9999999. And so this is getting close to 3.9, right? It's getting close to 4. Right? We're just plugging in 3. You're not plugging in a number that is significantly less than 3. So here's what you could say at this point if you really wanted to stop doing it. You could say either the limit's going to exist, and since the left-hand side is 4, for the limit to exist, the right-hand side would have to be 4, which would mean that the function is not continuous because the limit's 4 and the function is 2. Or the other option is the limit doesn't exist because the right-hand limit isn't 4, and then the function is not continuous because the limit doesn't exist. So either this function is discontinuous because the limit doesn't exist, or it's discontinuous because the limit exists and it's not the same as the function value. So once you've gotten to the place where the function is something and either of the one-sided limits is not that something, we know we're in a discontinuity. The small issue, not issue so much as, if I were teaching the class, I would want the students to tell me in what specific way it is discontinuous. Is it discontinuous because the limit doesn't exist? Or is it discontinuous because the limit and the function aren't the same? So I really think you should err on the side of showing your work, and seeing what the other side of the limit is doing. So if we look at the right-hand side of the limit as x approaches 3 from the right of f of x, that's, I mean, we know what's going to be different, right? We saw the picture. From the left, it's going to be 4. From the right, it's going to be 2. That's going to be the limit as x approaches 3 of the square root of x plus 1. So right in there. And then we just plug in 3. We get square root of 3 plus 1, which is 2. And now we can say, oh, f of x is not continuous at x equals 2 because, sorry, at x equals 3, apologies, because the limit as x approaches 3 of f of x does not exist. Right, the left-hand limit and the right-hand limit don't match up. Since I'm going to talk about this topic today anyway, I should also mention that there is something called one-sided continuity. So I would say that this function at 3, this function is right continuous because the limit from the right is equal to the function value. The limit from the left is not equal to the function value. So this function is right continuous at 3. And to be continuous at a point, you have to be right continuous and left continuous there. That's not usually how we define continuity, but it is a way of defining continuity. So, yeah, so this function is right continuous at 3. It is not left continuous at 3. And that's because the right-hand limit and the function value are the same. And that is an important idea, kind of. It's kind of like those limit rules. It's one of those things that we're kind of use all the time without ever actually thinking about using it. I'll say more when we get there.
I have a question.
Yeah.
So one of the questions I was confused on is like when we're giving it like different equations, like just exactly like that problem, except when they're asking if like f of 1 does that exist or is it continuous? It doesn't fit in any of the intervals. So how would we solve that?
So like they're saying maybe, so let me just modify this one slightly just so I can kind of answer the question. Let's say I change this to be like this. I want to make sure that I've got this right, Sarah. So is this kind of what you're saying? Well, so let me really go a little further. So let me say, if I ask now, is this function continuous at 3? The answer would be straight away no, because f of 3 doesn't exist, right? None of these intervals have x equal to 3. And so if that number isn't included in one of the intervals in your piecewise function, it can't be continuous there because it doesn't exist there. So if we wrote it like this, we would say, oh, f of x is not continuous at 3 because f of 3 doesn't even exist. Is that kind of what you mean?
Yeah.
Okay.
So it had to exist at 2 points.
Well, at 1 point.
Or 1 point, but from 2 directions.
That's less. That is not quite so true. So I feel like a lot of people have questions about this. So I'm just I was gonna do something else first, but I'm gonna jump straight to it. So let's look at this next example. Oh, they're gonna erase that. That doesn't really matter. It's not erased. So let's look at this function, which is a very kind of standard example. F of x equals to the square root, let's say 25 minus the square root. And the question here is, where is this function continuous? So really, again, when I read that question, what I really hear in my mind is, where is it not continuous? And so where does this function not exist, first of all? Well, we have some domain restrictions, right? We know that this function, we have to have a domain where 25 minus x squared is greater than or equal to 0. So it looks like x is going to have to be between 5 and negative 5. But you can do more work, right? You can factor this and say it's 5 minus x times 5 plus x. Be careful, I've definitely seen people factor this the wrong opposite way as x minus 5 times x plus 5. It's always the first thing, square root first. And then you could use the number line. Say x5 negative 5 is what makes it 0. And if x is bigger than 5, like 6, you get a negative from the positive, which is negative. If x is equal to 0, positive times positive. If x is negative 6, positive, negative. We want it to be positive, right? Because it's greater than or equal to 0. So this is definitely defined or has a domain on negative 5 to 5. And I will just say this probably many, many times actually. Most functions we see are usually defined on their domain. Are usually continuous on their domain. Not every single function, but the majority of functions we look at is often a pretty good bet that on their entire domain, or maybe with one or two exceptions, they're going to be defined and continuous on their domain. This one is continuous on the domain, but there's a little bit of trickiness to that statement. If I was going to graph this, do you guys know what kind of graph this has? What kind of shape we are all very familiar with, even if you might not recognize the graph? It's a shape I'm sure is in your room. It's a shape that is on my watch face. It's a circle. Well, it's half a circle. It might be easier to see if I rewrote it as y equals to the square root of 25 minus y squared, x squared, and then square both sides. Y squared is 25 minus x squared, and then add x squared plus y squared equals 25. Oh yeah, that's definitely a circle. Center is 0, radius is 5. The only difference is that this thing here is only has the possibility of y or f of x being positive. So this is just the top half of the circle, or the semicircle that's above the x-axis. So here's what this looks like. I should just draw first before I start doing things. This is the point negative 5, 0. This is the point 5, 0. This is the point 0, 5. And the question that I imagine many of you might have is this function continuous at that point and at that point? And please let me know if this isn't an issue, but I'm thinking this is where some of this confusion is coming. And so here's the answer. The answer is yes. This function is continuous at that point, but there's actually a nuanced definition here, but I think we need to address. So here's what I would say. For any point, for any x in the open interval from negative 5 to 5, so like, this point here, this point here, this point here, this point, any point except for the endpoint, it definitely looks like this is continuous. F of x is continuous at that point. For example, x equal to -3. The function is definitely continuous at -3 because 1, f of -3 exists. It's equal to the square root of 25 minus -3 squared, which is the square root of 25 minus 9, which is the square root of 16, which is 4. And 2, the limit as x approaches -3 of the square root of 25 minus x squared. Well, we can evaluate that limit by just plugging in -3, right? There aren't any weird 0 over 0 things, so we plug it in and we get 4 again. The function exists at -3, the limit exists at -3, and they're equal to each other. So the function is continuous at -3. And we could have picked any point, right, that wasn't -5 or 5. All right. I should say any point in the domain that wasn't -5 or 5. So what's the deal with 5 and -5? Well, let's take a look. All right. Let's look specifically at 5. If this is what we did down here. So is f of x continuous at 5? So let's find f of 5. F of 5 is the square root of 25 minus 5 squared, which is the square root of 0, which is 0. Check. All right. We're going to talk about the limit, and this is where things are going to be a little bit weird. So thing 2. The limit as x approaches 5 from the left of, it's not a piece, so I can just write the function. The square root of 25 minus x squared. Okay, I'm approaching 5 from the left. I know my 5 looks like it's got an extra big gap, but that's a 5 from the left. So x is a little bit smaller than 5. So I can just plug in 5. 25 minus 5 squared is 25 minus 25, which is 0. Okay, now here's the weird thing. The limit as x approaches 5 from the right. And this is kind of a subtle point here. This limit does not exist. Why, you might ask, right? Still, it seems like I should be able to plug in 5, and 25 minus 5 squared is 0, and square root of 0 is 0. But here's the thing, and here's where we actually have to think about that we are on the side of 5 where we're a little bit bigger than 5. If I'm bigger than 5, I'm out there. I'm not in the domain of the function. Or if I plug in a number slightly bigger than 5 here, I got the square root of a negative number. Right, so since I'm approaching from the side where the function isn't defined, that limit doesn't exist. Right, there are no y values of the function. Or there's no function that's like getting closer and closer to 0 from this side. It just doesn't exist on that side. Now, here's the thing, and I should kind of defer to the textbook here because I want to say this exactly right. That's not the right textbook. Let's look at the right textbook. One sec. Because there's a very specific thing that they say. Yeah. Right. So for an endpoint of a domain, so this is in my, I have, which edition of the book here? I have probably a slightly old edition. I can't even see the number on it. 12th, I have the 12th edition. I think you guys have the 14th. This is in the beginning of section 2.5 on continuity. There's a definition of an endpoint. And so the function is continuous at a left endpoint, or is continuous at the right endpoint if for the right endpoint, the left-hand limit is equal to the function value, or the limit as x approaches your endpoint from the left side is equal to the function value. So the point here is, the point is that we say that this function is continuous at this endpoint because the left-hand limit is equal to the function value. So we don't need this. This is kind of not important at all. And in a similar way, we would say f of x is continuous at x equal to -5 because f of -5 is equal to 0. And the only limit that matters, which is the limit as x approaches -5 from the right-hand side of our function, is also equal to 0. So if you're at an endpoint, you're continuous at an endpoint as long as the limit exists from the side that makes sense for it to exist from. Yes, right, exactly. To show continuity at this point, you only have to show these two things. You only have to show that these two things are equal. That the function is equal to 0 or whatever it's equal to, and the limit from the left has the same value. Yeah. On the other hand, and so this is kind of a really important point. If I instead define the function, let me define a new function. So if instead I said my function was some piecewise thing, f of x is equal to, I'm gonna have that same function in the middle. Then after 5, it's gonna be and 4 or 5, -5 is going to be, I don't know. So now we don't get to be so loosey-goosey with the 5s, right? Here, let's say, okay, is f of x continuous at 5? Well, since this function now is defined on the right-hand side of 5, I do have to look at the left right. So basically, if you've got something that's only defined from end to end, you get to say it's continuous at the endpoint if the limit from the appropriate side exists in the equal function value. But if you've got something that's defined on either side, even if this function kind of has a natural barrier endpoint at 5, you still have to look at the limits that you usually do. So here, you'd say, okay, f of 5, plug in 5 here, you still get 0. And then the limit as x approaches 5, well, I do the limit as x approaches 5 from the left of f of x, which would be the limit as x approaches 5 from the left of this function. And I would just plug in 5, 25 minus 25 is 0, so 0, 0. And then the limit as x approaches 5 from the right, I would use this piece. I would plug in 5, I'd get 2 to the 5th minus 32, which is 0. So the left-hand limit and the right-hand limit are matching up. So this, at least the right-hand side of this, looks something like, okay, here's my half circle from -5 to 5, and then this 2dx minus 32 is doing something like this. So it is continuous there. It's not differentiable, but that's another story. It's not differential because you have a pointy point, or a cusp is the more normal word to say, but I like to say pointy point, so you're probably going to say pointy point. On the other side, at -5, I'm pretty sure that function is the function is not going to be continuous there because room. I have no room. Let me start thinking. So f of -5 is also 0 because I plug in -5 into that function. And then the limit is x approaches -5. Well, the limit from the left, right, if we approach -5 from the left, so if we're coming at -5 from this side, we're using this piece of the function. If I plug in 3 times -5 is -15 plus 1, which is -14. So this does something like, my scale is too small, but it's something like way down here. Right. It does that kind of deal. So this function is defined everywhere, but it's clearly not continuous at -5. Because the left-hand side and the right-hand side are not meeting up.
Wait, why do we use the equation 2 squared 2 to the x minus 32 when we're evaluating as x approaches 5 to the right?
Well, because we're approaching 5 from the right, so we are bigger than 5, and that's this.
But isn't like if it's a less than and not equal to, it doesn't include the 5.
So when I'm trying to find so if I'm finding the limit as x approaches 5, right? Taking the limit as x approaches 5 from the left. So again, this here, when I see 5 from the left, I'm really thinking, okay, x is less than 5. So I'm using this part right here, which means I'm using that function right there.
Oh, okay.
But when I'm doing the limit as x approaches 5 from the right, I'm thinking, oh, x is bigger than 5. So I'm approaching 5 from the right-hand side, right? Because I'm really, when I'm thinking on the right of 5, I'm just thinking of the number line, right? If this is 5, I'm on this side of 5, like 6 and 7 and a million. So if x is bigger than 5, I'm using this piece of the function. So that's why I'm using that piece there. Other questions about this?
I'm still confused why the function of -5 is not continuous.
So the reason that this function is not continuous at -5 is because, well, it's not because it doesn't exist, right? F of -5 certainly exists. F of -5 is equal to 0. I think my picture here is probably not the best. Let me erase that part. So here is the picture of the graph. I'm going to make this look a little bit nicer. But come on back, eraser. Right, that's my graph. So as I go from left to right, I'm traveling up this line, and then I get to this point, and I have a jump discontinuity from there to there. So graphically, we can kind of see, oh yeah, it looks like it's definitely discontinuous at -5. But here's the actual kind of justification. And I know I'm going to write anything. It's hard to see down here. So I guess I'll erase this part. Hopefully, I'm going to erase this part. So I'll do that. So all we're saying here is that we know f of -5 equals 0. The limit as x approaches -5 from the right. So again, remember, this means that x is bigger than -5. So if I'm bigger than -5, I'm using this piece of the function, right? Because x is bigger than -5. And then I just plug in -5. -5 squared is 25. 25 minus 25 is 0. The square root of 0 is 0. On the other side, and I do the limit as x approaches -5 from the left of f of x. My 5s from the left always look like it's just 5 that's missing spots. Okay. So approaching -5 from the left, which again means x is less than -5. Which means I am looking at this piece right here. So I'm looking at that piece right there. So that's the limit as x approaches -5 from the left of 3x plus 1. And then I just evaluate the limit in the usual way, if I can, by plugging in x equal to -5. So I get 3 times -5, which is -15, plus 1. which is negative 14. So this point here, which is filled in, is negative 5, 0. This point here, which is not filled in, is negative 5, negative 14. But then I can say that this function is not continuous at negative 5 because the limit does not exist. The limit is x approaches negative 5 of f of x does not exist. The left-hand limit and the right-hand limit don't match, right? They're not hitting each other. And that means that we're not continuous. And again, graphically, I think it's pretty clear, right? That, oh yeah, we're having this jump. We can't say it's continuous because we have to lift our pen off the paper to graph the thing.
Oh, so if there wasn't that function and it was just the semicircle, then negative 5 would be continuous.
Right. So you could totally, if you wanted to. So actually, let me answer a question about this, and then I'm going to modify things. So as is, here's what I would say about the continuity. I would say I'd love more room on the board. I would say that this function is continuous on the following interval. So it's continuous on the interval from negative infinity to negative 5, excluding negative 5, and then everything from negative 5 to infinity. So this function, as written, is continuous everywhere except for negative 5. Okay. Check this out. I want more room. Fine, other side of the board. If instead I totally cut off this first section of the piecewise function, so if I said that my function, I'm going to call it g of x, was equal to just these two pieces, and then the other piece, which looks like this. I would say that this function, g of x, is continuous on the interval from negative 5 inclusive to infinity. Because now, since this function isn't defined on the other side of negative 5 is an endpoint, and as far as an endpoint is concerned, as long as the limit from the other side exists and is the same as the function value, you have continuity at that endpoint. So this function is continuous at negative 5. This function is not continuous at negative 5. Kind of weird. That you can add a piece to a function that's continuous at the point and make it discontinuous at that point. All right, let's look at another example, a different example, but still in the same realm of work. Let's look at the function. How fun do we want it? Sure, let's make it real interesting. Sine squared of 5x over 3x squared. Okay, here is the question. Where is this function continuous? Let's get rid of this pen. Okay, so you know what my question really is. Where is this function not continuous? I bet you guys have a guess. I bet it's right. Where is at least one place where this is discontinuous? Yeah, exactly. And it's actually continuous everywhere else, right? Sine is a function that is defined everywhere and is continuous everywhere. Sine squared is also continuous everywhere. Sine squared divided by something is continuous as long as it exists. So it's continuous as long as x isn't 0. So we could say this is continuous on the interval from negative infinity to 0, union 0 to infinity. And it's discontinuous at 0 because f of 0 does not exist. Right? You get 0 over 0, which is undefined, indeterminate. All right, well, what if I did this? What if instead I said, okay, now instead, I'm going to redefine f of x to be this function, sine squared of 5x over 3x squared, as long as x is not 0, and 5/3 when x is 0. Now is this function continuous at 0? It's a good question. It's kind, so I'm not going to lie, it's kind of a trick question. I'm going to warn you right now. The answer is no. It's not continuous the way I've written it. I know, right? You guys are like, huh? Remember, so it's not, here's what I'll say. If it was sine of 5x over 3x, then yes, it would be continuous because the limit would be 5/3. But sine squared of 5x over 3x squared has a different limit. But let's go through the process and see. Because I know there's a question on at least the Haas homework that's basically like, if you have a function like this, how do you fill in the missing point so that it is continuous? And really you fill it in with what the limit's equal to. So part 1, f of 0 exists. Of course, right? All right, we're not doing this one anymore. We're doing that one. F of 0 is just 5/3. Easy peasy. All right, part 2. Does the limit exist? So here's a nice thing about this piecewise function. On either side of 0, either when x is bigger than 0 or when x is less than 0, you still have the same other part of the function, right? This function is equal to sine squared of 5x over 3x squared when x is less than 0 or bigger than 0, which means we don't have to look at the one-sided limits here. We can just say, well, I'm going to look at the limit as x approaches 0 of sine squared of 5x over 3x squared. And then we're going to use our rules for dealing with these limits of sine of something over something, right? Where we want to have sine of a thing over the same thing, as long as that thing is going to 0. So I want to re-express this as the limit as x goes to 0. Sine squared of 5x is sine of 5x times sine of 5x. And then dividing by 3x squared is like multiplying by something over 3x squared. And again, I'm going to use my wish method. What do I wish I had beneath sine of 5x? I wish I had 5x. If I wish for one there, I have to put one there. And I wish I had the same thing down below here. I wish I had a 5x down here. But if I have a 5x down there, I also have to put a 5x up here. All right, so now everyone should be able to tell me what this limit is. The limit as x goes to 0 of sine of 5x over 5x is 1. The limit as x goes to 0 of sine of 5x over 5x is 1. And then 5x times 5x over 3x squared simplifies to 25/3. And so my whole limit is 25/3. And so again, I've definitely seen people say, oh, the limit exists, the function is continuous. It's not the case here. The limit exists, the function exists, but they're not the same. So here we would say, f of x is still not continuous at x equals 0. because the function value and the limit value are different. And so then the final question that someone would probably ask you for this is, okay, how do you, what's what I'm looking for? I had something written here and I totally lost it. Oh yeah. How do you define a continuous extension of this function? Meaning, how do you define this function at 0 so that it is continuous? And the answer, obvious, maybe not obviously, but I feel like it's obvious. The answer is that you have to define the function to be equal to what the limit's equal to. So instead of 5/3, we would define it to be equal to 25/3 at 0. And that would make it continuous. Functions like this that have what are called point discontinuities, where you just are essentially you have a function that's continuous and you remove one point from it. Those are called point discontinuities, and they do have what's called a continuous extension, where you can say, oh, I can fill in that one point and make the function continuous. All right, we're back. We have a cat. She really would like to sit in my lap all day. That is not an option because I have to teach math. So say goodbye to Sparky, the noodle, as we often call her. She will probably meow after me in my lap again, but that's all right. Yes, she is adorable. She's an old lady. She is, I don't know, she's pretty old. She's, I think, 16 or 17. Yeah, she's getting up there. So, yeah. Kate, my wife and I have had her almost the entirety of our relationship. And yeah, she's a pretty great cat. Okay, yeah. All right, let's talk more about things that are mathy. I feel like, yeah, I mean, continuity, did you have something, William?
Yeah. On my homework, I have a problem that I'm not quite sure how to attack. Show that the equation cosine of x equals x has at least one solution.
Excellent segue. Such a good example. I mean, it's a very standard example, but I'm glad you asked this question because it really gets at the next thing we want to talk about, which is the intermediate value theorem. So I'm going to come back to this in a second. So let's look at this example. Let's say we have the function f of x equal to, I don't know, something not particularly exciting, x cubed minus 7x plus 2. And I want, well, here's what I'm going to tell you. Here's what we can say. We can say that f of, I don't know, f of 2, sure, f of 2 is equal to 8 minus 14 plus 2, which is -4. And f of, I don't know, what do I want to pick here? Sure. F of -1 is equal to -1 cubed, which is -1, minus 7 times -1, which is plus 7, plus 2. That's equal to positive 8. So f of -1 is equal to 8. F of 2 is equal to -4. So why must it be true? Why must f of x equal to 0 have a solution? Why does this function have to equal 0 somewhere? Well, here's what we've got. I'm going to try and draw a picture here. I've got f of 2 equals -4, so I'm not going to draw a great picture. So here's f of 2 equal to -4. And f of -1 is positive 8. So let's maybe like -1, 8, sure. So we know our function goes through these 2 points. So why can't I just do this? Why can't I come down part way and then maybe jump down here like that? Why is that not an option for this function?
It's continuous.
Right? If a function's continuous, you can't just jump over some of the y values. You have to hit all the y values, in this case, between +8, and -4. Specifically, we have to hit the y value of 0. And this is the whole idea behind the intermediate value theorem, that if you have a function that is continuous between 2 points, you have to hit every intermediate value between the two y values. So I can't really draw it like that, right? What we actually have to have is that this function does something like, right, like that. I don't know exactly what this function, my picture I'm sure is not very good. Right? It probably does something more like this. Whatever, that's not the point. The point is that between here and here, I get every y value between -4 and +8. I get -3, I get -2, I get pi, I get e squared. Yeah, e squared is less than 8. All right, I get everything you could want between -4 and 8. Specifically 0. 0 is the one we're usually most interested in getting because it's easiest to kind of think about, well, I know I get 0 if somewhere the function's positive and somewhere the function's negative. If I go from positive to negative, I have to hit that 0, which is in between. So let me actually kind of show you how you would actually prove that this function has a solution. So here is how you would write up a proof that this function x cubed minus 7x plus 2, I should really say that this equation x cubed plus 7x minus 7x plus 2 equals 0 has at least one solution. It probably has 3 solutions because it's a cubic function and I think it hits the x-axis 3 times. Doesn't really matter. So here's how I would do it. Step 1, observe. F of x is continuous. The function only has to be continuous on the interval that we're interested in looking at. But more is never a problem. This function is continuous everywhere. Just like any polynomial is continuous everywhere. Okay, then to make sure that it equals 0, we have to find a place where it's bigger than 0 and a place where it's smaller than 0. You can use these values. You could use other values as long as you could find one where it's positive, one where it's negative. So if I hadn't given you these 2 points, I probably wouldn't come up with those. I would probably start with plugging in 0. So note that f of 0 is 0 minus 0 plus 2, which is positive. And then I would probably try plugging in 1, and I would get f of 1 is 1 minus 7 plus 2, which is -4. Oh, did I? No, I didn't. No. Interesting that plug in 1 or 2, you get -4, which is negative. So then, since the function is continuous, and it goes from a positive value to a negative value, by the intermediate value theorem, there has to be a number between 0 and 1 where the function is equal to 0. So the way we usually say this is by the intermediate value theorem, which we almost always abbreviate as IVT, there must exist a number. We usually call it C, such, and I also, you don't have to say this, but I usually like to say where C has to live. So in this example, right, f of 0 is positive, f of 1 is negative. So C has to be between 0 and 1, which I happen to actually draw my picture so it looks like that. So there is a C between 0 and 1 such that f of C equals 0. And that's it. We have shown, using the intermediate value theorem, that this equation has to have a solution. I will point out we don't know what that solution is. We almost never actually know what that solution is when we're using the intermediate value theorem. That is usually the gist.
We never have to find it.
Correct. I should say, it's not that we can never find it, it's that most of the time we can't find it. So in fact, if you want, we can totally, I mean, you can look at a graphing calculator, right? So we could definitely look at this function on Desmos. X cubed minus 7x plus 2. And here's the problem with at least functions of degree higher than 2, or I should say polynomials of degree higher than 2. Unless I happen to pick something magically nice. No, I did not. So solving a cubic function is really, really challenging. Like, depending on, I mean, sometimes they have nice solutions, but sometimes the solutions are very, very complicated. And so here, the decimal approximation is 0.289. But I don't know, I mean, it's not really 0.289, right? If you plug that in, you wouldn't get exactly 0. It is some irrational number that is actually quite complicated, like honestly, graduate level math complicated to figure out how you actually solve this equation equal to 0. Believe it or not. I didn't believe it at first until I learned about it. It's like, holy smokes, this is some weird stuff. So yeah, solving higher degree polynomials can be very, very challenging. But that's not what we're being asked to do here, right? We're just being asked to show that there is a solution. So I don't know what the solution is. I mean, I know it's about 0.289, but I know for sure it's between 0 and 1. Or I could have even said it's between -1 and 2. That would have also been a sufficient thing to say. So now
on the other side
yeah.
of the board. So for 0 and 1, we don't have to pick those numbers. So like if let's say we had a different equation, we could pick whatever just like shows the negative and the positive value.
There's only two things you have to be, yeah. So you need to pick numbers. So yes, because usually we are always going to reframe the question so that we're trying to solve an equation equal to 0. And 2, the only limiting piece of the only limiting requirement there is that you have to make sure that you're picking numbers that are in an interval where the function's continuous. Most of our examples are going to be continuous everywhere. Like the next example on the other side is definitely continuous everywhere. But there are some functions that are not continuous everywhere that you can still show you can solve by using the intermediate value theorem. We'll do one like that after this next one. So, yeah. So here's how you do this. And so sometimes, so these questions kind of work out differently depending on what you're given. Sometimes they'll just give you this, and this is kind of the bare bones, least amount of information you can be given. Slightly more is sometimes they can say, show that this equation has a solution on an interval. Like I can say, show that this has a solution on the interval from 0 to 1. That's also an option depending on what's given. So here's the first step. I don't want to try and show that, right? Right? To do it like this, you have to be like, okay, I need to find a place where this is bigger and where this is smaller. It's much, much, much simpler to just say, I'm going to rewrite this, right? I'm really trying to solve, or I'm really trying to, I'm not actually trying to solve, I'm trying to show that this equation, cosine of x minus x equals 0, right? That would be equivalent as showing this as a solution, showing this as a solution. Okay, so typically what we're going to do is we're going to let f of x equal the function that we're trying to show equals 0. It just makes it notationally more simple to call the thing f of x instead of saying cosine x minus x every time we're trying to plug in a point. Okay, so it is always important to make, I think at least, and I feel like the teacher probably agrees, you somewhere need to say that you know this function is continuous either everywhere or at least specifically on the interval that we're going to end up using. If it's continuous everywhere, just say it's continuous everywhere. And this is. Cosine, we know what cosine looks like. Cosine's continuous everywhere. X, also continuous everywhere. And then if you subtract two continuous functions everywhere, they're continuous everywhere, right? Or as I think I don't remember if it was this class or a different class. When you add or subtract functions, they are, right? The domain of them is the intersection of their domains or the overlap. But since both of these have the domain that's everything, the domain's everything, and so they're still continuous on that domain. Basically, when you add or subtract or multiply functions that are continuous, it's still continuous. If you divide them, you have to be worried about the denominator being 0, right? Like x divided by cosine x would not be continuous everywhere because it's going to be undefined when the denominator is 0, like when x is pi over 2 or 3 pi over 2 or 5 pi over 2. But that's not the problem here. So this is continuous everywhere. So we have to make note of that. I usually like to say, observe that f of x equal to cosine x minus x is in fact continuous everywhere. We can say continuous on the interval from negative infinity to infinity. Great. Our only other job is to figure out a place where this thing is positive and where this thing is negative. So I usually start by trying to plug in 0, unless it's not an interval. But if 0 is in your, right, so if this wasn't given to me, I would still try 0. If that was given to me, I would try 0 because it's one of my endpoints. The only time I wouldn't try 0 is if they said, you know, the interval is from like 1 to 2 or something that didn't include 0 in it. So I'm always going to be plugging in 0 because it's easy to plug in 0. So cosine of 0 is
1, right?
Yeah. So we get 1 minus 0, which is 1, which I don't really care that it's 1 so much that I care that it's positive. Okay. So now our job is to pick another value of x that we can plug it in and get something negative. And this is a little bit more challenging. There's a couple ways you could go here. You could either try plugging in 1, but I don't know what cosine of 1 is. We'll address that in a minute. Really, you could pick anything. So I'm going to pretend like we're not stuck with this interval, right? We're not limited to this interval. We can do anything we want. So let's go big. Let's try an f of, that feels like I'm cheating. If I went f of 2 pi, cosine of 2 pi minus 2 pi, cosine of 2 pi is 1, right? It's the same as cosine of 0. 1 minus 2 pi is definitely negative. So I could certainly say by the intermediate value theorem that there is a solution to this equation, and that solution is some number between 0 and 2 pi. But I'm gonna.
So if we have the interval given to us and it doesn't include a negative, then we use 2 pi to get a negative.
So here's what I'm saying. I'm saying if you're not given an interval, just try and find some number where it makes it negative. But let's back up. Let's say instead, yeah. I feel like, let me think for a second. Yeah, this is always the one. I'm trying to make it kind of harder. So now let's actually go back to 0, 1. Yeah. Let's say I'm gonna make it slightly bigger. Sorry, I have to think for a second. No, they're all too, yeah. Let's go back to 0, 1. So I certainly could try plugging in 1, but that's challenging, although we will do it in a minute. So if you can't use your endpoint because it's weird to plug in or hard to evaluate, you can pick a number smaller. What's a number smaller than 1 that I can actually find cosine of relatively easily? Well, pi over 4 is less than 1. And I know how to take cosine of pi over 4. So f of pi over 4 is cosine of pi over 4 minus pi over 4. Now this is still going to be kind of weird to evaluate. Cosine of pi over 4 is root 2 over 2 minus pi over 4. So I need a common denominator. This is going to be 2 root 2 over 4 minus pi over 4. Okay, so let me ask you guys a question. Is 2 times the square root of 2 minus pi positive or negative? So here's the way I would kind of think about it. I know from lots of putting it into a calculator that the square root of 2 is about 1.4. So 2 times the square root of 2 is about 2.8. 2.8 minus pi is definitely less than 0 because pi is bigger than 3. So this is definitely negative. Yeah. Yeah. Here's what I'll say. You could also do it for 1, right? F of 1 is cosine of 1 minus 1. Now, I don't know what cosine of 1 is, but I do know that it's less than 1. Because cosine of 0 is 1. Cosine of 2 pi is 1. And that's the only times when cosine is equal to 1. When you're, am I going the right way around my circle? Does this look like the right-hand side of my unit circle? Have we got it backwards? Okay. Sorry, it's always super weird when I'm looking at myself on the thing. So here's cosine of 0, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. This is where cosine is equal to 1 at 0 radians and at 2 pi, which is about 6.28 radians. And any other radian value that's not 0 or 2 pi, like 1, which is about right there, cosine is going to be less than 1. So I can say, hey, this is for sure less than 1 minus 1, which is 0. So I know I've kind of said a lot about this particular problem. The point is, you could use any one of these points. If you're given a specific interval, you have to be a little bit more choosy. If you just can work with anything, I would probably pick 2 pi, because 2 pi seems easy. But so then I should get to the sum up. So yeah, let's sum up. So I feel like you should definitely write these words at the end of an intermediate value theorem. So we can say, since f of x is continuous on the interval that we're going to use, I'm just going to use the write an interval. Let's say 0 to 2 pi. And f of 0 was 1, which is positive. And f of 2 pi was 1 minus 2 pi, which is negative. Then by the intermediate value theorem, there must be a number c such that, I always forget, the number c between 0 and 2 pi, between the x values we plugged in, such that f of c, which is cosine of c minus c, is equal to 0. Or in other words, c solves cosine of x equals x. This part up here that I wrote, you didn't really need to write that again because we already kind of said that already, but I felt like I should write it again since you're on the new side of the board. So that's the idea with intermediate value theorem. You say the function is continuous, you show it's positive somewhere, you show it's negative somewhere, and then you say by the intermediate value theorem, there has to be a place between those two numbers where it's positive and where it's negative, where it has to equal 0. That's the whole gist.
So even if in the interval there's no like negatives in it, there is a number in the interval where you plug it in and you can get a negative value.
Because we're not saying the inputs have to be negative, we're saying the outputs have to be negative. Because we're saying you're trying to show that the function, aka the y value, has to equal 0. So you're saying, oh, there's somewhere where the y value is positive and somewhere where the y value is negative. And so since the y value goes from positive to negative, we have to hit 0, which is in between those two things.
Okay.
Let's look at another example. Let me think of another example. So typically these functions that you're given are not going to be functions where it's easy to just like try and solve the thing. Yeah. For example, sure. Show that x equals to e to the negative x has a solution. We know it does. Well, maybe we don't. Maybe we should talk about how we know. I think I know it does because I know what the graphs look like, right? I know that y equals x looks like that, and y equals e to the negative x looks like that. So if I had to guess, I would say my guess was going to be somewhere, my solution was going to be somewhere between 0 and, I don't know, some positive number. But I would definitely pick 0, where e to the negative x is clearly larger. And then I would try to pick something out here where it's going to be the other way around. First things first. We're going to really try and solve, or we're going to try and show that instead of this, we want to show that x minus e to the negative x equal to 0 has a solution. We always want to set it up so that it's something equal to 0 has a solution. Okay. So then, note or observe, say something about how the thing you're trying to show is equal to 0 is continuous. And call it f of x or g of x or whatever letter you happen to like the best. So note, observe that this function is continuous everywhere. Oh, I was going to do an example where it wasn't continuous everywhere. Oh well, I didn't do that next. Okay. Also see that f of 0 is 0 minus e to the 0, which is negative 1, which is negative. And I don't know how big I have to go for this next one. You could try f of 2. F of 2 is 2 minus e to the negative second, which is 2 minus 1 over e squared. Is that positive? Yeah, right? 1 over e squared is pretty small. 2 minus 1 over e squared is definitely positive. Great. We're done. I mean, we're almost done. Then we should say something like, by the intermediate value theorem, there is a number, we call it C. C is between blank and blank, such that you can either say f of c equals 0, or you can also say that c is a solution to your original equation, x equal to e to the negative x, or f of x equals 0, whatever you want to write, right? You're just saying that there's a solution. Okay, did you guys fill in the blanks? Where does my c, so the way I've done this problem, c is between what and what? You can write it in the chat, say words.
Is it negative infinity to infinity?
Not negative infinity. I want to be a little more specific. What numbers did I use?
0 and 2.
Exactly. Right? I showed that f of 0 was definitely positive. I showed that f of, I don't know, I'm going to say it's like, right? Well, actually, I shouldn't say, that's actually not f of 0, right? I'm not actually graphing f of x here. So I know that, right? Oops. So I know that between 0 and 2, at 0, I said positive, but I should have said negative, right? At 0, my function, which is x minus e to the negative x, is negative because this is smaller than that. And over here at 2, x minus e to the negative x is positive. So somewhere between those two, x minus e to the negative x had to equal 0. It's literally where they intersect, right? That's the point. I just don't know what it is. We don't have to know what it is. Okay. I did want to show you one more example just because sometimes we do have to be a little extra careful. So let me show you one more. Then we work on it.
In that problem, was e just a variable, or is it?
E is never a variable. E is a constant. So E is the natural base. It's approximately 2.7. So like when I say natural log of x, I mean log base E of x. Like that's where E shows up a lot. Let's see, I was going to come up with a good question. Sure. All right. This one, this one's probably going to suck. It's all right. Sometimes they suck. So show that, sure, f of x, not f of x. Show that, yeah, okay. Secant of x, all right, equal to 2 minus x has a solution on the interval from 0 to pi over 2. So here's the thing to be aware of. We can't plug in pi over 2. Right? Pi over 2, secant isn't defined at pi over 2. But let's start off with the usual process. We really want to solve, so we're, in fact, this is that kind of step 0. We really want to show there's a solution to secant of x plus x minus 2 equal to 0. That's what we're really trying to do, because that's easier. It's always easier to show there's a solution to something equal to 0. Okay. Is this function continuous? Yeah, it's continuous on this interval. It's not continuous everywhere. Right? Secant is definitely discontinuous at a lot of places, like any odd multiple of pi over 2. So that's okay. They gave us an interval to work with. So I know that this is definitely, so f of x, which is secant of x plus x minus 2, is continuous on the interval from 0 to pi over 2. Now, usually they give you a closed interval so that you can actually just try plugging in the left endpoint and the right endpoint. We're going to have to work a little harder here, right? Because plugging in the left endpoint is fine, but I have to find something smaller than pi over 2. Okay, so what's f of 0, right? I'm always picking 0. 0 is almost always, without a doubt, a great choice. So what do we get when we plug in 0? And specifically, what's secant of 0?
It's also 1, right?
Yeah. So I get 1 plus 0 minus 2, which is negative 1. So now we're looking for another number that when I plug it in, it's going to end up being positive. So I'm going to try picking things that are easy to take secant of. I would probably try pi over 3, because I know that pi over 3 is less than pi over 2. Right, so we're still in the interval where we're continuous, right? You have to pick things in the interval where it's continuous. And furthermore, I know that cosine of pi over 3 is 1/2, which is going to be easy to take the reciprocal of. We also get to try pi over 6, but cosine of pi over 6 is √3/2, and the reciprocal of that is just less nice. So let's try f of pi over 3, which is secant of pi over 3 plus pi over 3 minus 2. Okay, so let's see, secant of pi over 3 is 1 over cosine of pi over 3 plus pi over 3 minus 2. Cosine of pi over 3 is 1/2. 1 over 1/2 is 2. So I get 2 plus pi over 3 minus 2. And lucky us, the 2's cancel, and we just get pi over 3, which is definitely greater than 0. That worked out. So then we would finish this off, right? We would say, okay, we found a place where it's positive, we found a place where it's negative, we know it's continuous. Those are all the pieces we need to say that this function has a solution. Sorry, say this function has a solution, not is anything. So then, this part just starts to fill. By the intermediate value theorem, there exists a number C, and I'm specifically going to say it's between the two numbers I picked. So I'm going to say C is between 0 and pi over 3, because those are the values I plugged in to get a negative thing and a positive thing. It would also be correct to say it's between 0 and pi over 2. But I usually think it's nicer to opt for the smaller window of where your solution is. And if I'm trying to say there is a solution, it seems nice to err on the side of being more precise by giving a smaller window if possible. Not required, just nice. Such that f of c equals 0. Or if you prefer, c solves secant of x equal to 2 minus x. So somewhere between 0 and pi over 3, there's a solution to this equation. Do we know what it is? No, we don't. That's okay.
So we could use 0 to find that there's a wait, why do we use 0 if we're trying to find for 0?
So there's two different things going on here. We're trying to show that this is equal to 0. Actually, you know what? To answer your question, let me actually just try to throw another example at you. Not that we'll finish this one, just that, so let's say I wanted to show that f of x equal to that 1 over x equal to natural log of x. Let's make sure that definitely has a solution. Has a solution. Okay. So 0 is not an option to plug in here, right? But I mean, so in fact, sorry, I'm kind of all over the place here. Right? If I'm, you know what? Let's use nice graphing tools as opposed to my limited graphing skills. Let me just show you. So here's what I mean. Yeah. Come on. Yes, I've got all the things up. I don't need all you up. Okay, so here's what I want to really say. So I'm trying to show that secant x equal to x has a solution. There's good old secant, sorry, equal to x, 2 minus x. And there is, okay. So there's actually, I mean, there's a number of solutions, right? But I specifically wanted to be between 0 and pi over 2. So I can actually kind of show you. If you want to make a limited domain for a function on Desmos, you put it in braces. So that just gives me the portion we're actually working with. And then you can do the same thing here, although you don't really need to. Oops, not there. All right, so I'm trying to show there's a solution between 0 and pi over 2. So I plugged in 0, and I got that the blue one was bigger. And then I plugged in some number like pi over 3, which is somewhere over here, and got that the blue one was smaller. I could also graph the two functions together. Or I can graph, sorry, what f of x is. So f of x is, sorry, secant of x plus x minus 2. And again, let me just limit that domain there. Right, so we can see that for the green function here, right, we're trying to find or we're trying to show that this green function is equal to 0 somewhere. So I'm saying, well, okay, I'm trying to show that the y value is 0. So I plugged in x equal to 0, and I got -1. And then I plugged in x equal to, I wish there was a nice way to like plug in pi over 3. I don't know, maybe there is, maybe I'm just not smart enough. Maybe I can be smart here. No, I'm not that smart, sorry. Anyway, I'll just tell you, right? So there's 1, pi over 3 is a little bigger than 1. So like maybe I plugged in like right about there. There's probably pi over 3 somewhere in there. And I got a result that was bigger than 1, right? I think I erased it. Sorry. I plug in pi over 3, yeah, I erased it. But the point is, right, it's okay to plug in x equals 0. I can plug in x equal to anything that's in the interval that I'm allowed to work with. So I plugged in 0 because it's convenient. I plugged in pi over 3 because I thought it would get me what I wanted. And so there is a solution. It's about 0.696. I don't really care that what it is. I just care that it's between 0 and pi over 3. 0 is not always an option, but when it is, I like to choose it.
Oh, okay. I think I got mixed up with like if there's a value at like x equals 0, but we're plugging in x equals 0 instead of like when y equals to 0.
Yeah, so again, we're trying to show that y equal to 0 has a solution, but we don't actually plug in 0 for y and try and solve it, right? I'm not actually plugging in 0 here and actually able to find what x is. I'm just able to give a interval where there is an x, where if I knew what that x was, in this case, it's approximately 0.696, we could say that there would be a solution there. But I don't actually know what the number is. I just know that it's in some interval. Same thing is true here. I want to show that this has a solution. And now I know that I'm limited in my domain, right? I'm trying to show that f of x equal to 1 over x minus natural log of x. 0 has a solution. And we know that our domain here is 0 to infinity, right? Because the function is not defined when x is equal to 0 or negative. So I'm just going to try and pick things that are easy. And here is where some, oh, sorry, I should stop sharing my screen. Apologies if you did. Everyone's like, what's he writing there? Yeah, sorry. So this is where it's really good to have in your head ideas of what the graphs look like, because it's going to help you pick values. I know that 1 over x looks like this and has a point at 1, 1. I know the natural log of x looks like this and has a point at 1, 0. So I definitely know that when I plug in 1, I can see one of them being bigger than the other one, right? So I can see that f of 1 is equal to 1 over 1 minus natural log of 1, which is 1 minus 0, which is positive. And then I can definitely see that, okay, at 1 over x is the bigger function. And somewhere out here, they're going to cross. I would love to know what that point actually is. I'm not going to find it. But I just need to go far enough out so that then the logarithmic function is the bigger one and the 1 over x is the smaller one. So I'm going to pick a large number. Maybe e is big enough. So I'm going to pick a large number that's easy to take the natural log of. So I'm going to pick e. So f of e, which again is just about 2.7, is 1 over e minus the natural log of e. That's 1 over e minus 1. And 1 over e is definitely smaller than 1, right? 1 over 2.7 is about 0.3. I don't need to know what it is. I just need to know that it's smaller than 1 so that this is definitely less than 0. And there we have it. We can say, okay, I should observe. So first observe that f of x equal to 1 over x minus natural log of x is continuous. You could either say on the interval from 0 to infinity, or you could go smaller and say on the interval from 1 to e, since those are the endpoints we need to pick. And then f of 1 is positive, f of e is negative. So by the intermediate value theorem, there is a number between a c between 1 and e such that f of c equals 0.